Hello and welcome to the channel. In this video, we will take a look at the Incremental Source Generator API in C#. For this video, I am assuming that you know what a source generator is and what they are used for. The source generators added in .NET 5 did not support caching. As a result, your development environment could take a performance hit as you added more and more source generators either through your own code or through third-party libraries. To address these performance issues, incremental source generators was introduced in .NET 6. Incremental source generators take advantage of caching between each step of the generation process. This caching helps reduce repeating work by checking the cache and only run the generator if there has been changes to the code, and then only run the generator against code that has been changed. So let's get started setting up the project. As you can see, I have cheated a little bit and already set up the project. First and foremost, we obviously need the generator library itself. I've got it right here, and the first requirement for making incremental source generators is that the generator library is targeting .NET Standard 2.0. This is a hard requirement from Microsoft. The next thing to do is to install the following NuGet packages: Microsoft.codeanalysis.analyzers and Microsoft.codeanalysis.c#. These are the NuGet packages where the generator API is located. We set the private asset attribute to all because we don't want to expose these libraries to the consumers. The last thing to add to the generator's project file is to tell it that we don't want our analyzer code to be visible to the consumer project. We do this because generators are meant for the build process and not meant to be directly referenced in the consumer code. The next thing we want to do is to be able to debug our source generators. To do that, add a unit test project to the solution. I'm using XUnit, just because I'm more familiar with that one. But you can use NUnit, MSUnit, or whichever you like. This is not really that important. But what you do need to do is to add a reference to the NuGet package Microsoft.codeanalysis.c# and a reference to the source generator library. Once that is done, add a new class to the debugging project. I'm calling mine Generator Debugger and add the following method. Without going too much into details about the nitty-gritty of this particular code, essentially what it does is that it programmatically creates a C# compilation that uses our source generators, and because of this, it allows us to debug via the unit test debugging function directly from Visual Studio. We now have the bare minimum required to start developing our incremental source generators. However, for a reason I will go into later, I also recommend that you add a debug consumer project to the solution. For this video, I will just be using a standard C# console application. The consumer library also needs to reference the generator library. However, because we actually want to use the generators as generators in this project, we will need to modify the references a bit. The first modification we will do is to tell the project that this is a reference to an analyzer project. We will do this by setting the output item type attribute to analyzer. The second modification is to set the reference output assembly attribute to false. This causes the generator assembly to not be included in the output from this project, since we don't need it anymore at that point. Now that the project has been set up, let's create our first source generator. In the generator library, I have added a class called markerGenerator. This generator will be used to generate an attribute called onDisposedAttribute. This attribute will be used as a marker attribute for another generator. Markers is a way to tell the generator that this particular piece of code is relevant for its generation. A marker do not necessarily need to be an attribute. They can also be interfaces, member names, or something else that might be appropriate for your use case. However, the most common approach is to use attributes. Now, if we take a look at the generator code, you will see that it has the generator attribute. This is needed for the class to be recognized as a generator. On top of that, our class also needs the interface INCREMENTAL to make it an incremental source generator. Non-incremental source generators will use the interface iSourceGenerator. The INCREMENTAL interface also makes sure that the generator class exposes a void method called initialized that takes an incremental generator initialization context as parameter. This initialize method is where the magic happens. First, I have declared a variable called hint. This is the file containing the generated code. I have also declared a variable called markerSource. This is the source code the generator will output. In order to actually output some C# code, we need to register the output with the incremental generator initialization context. And since we don't need access to the consumer code base to generate our output, we'll register the output using the register post initialization output method. The register post initialization output method takes an action as parameter. The action itself takes an incremental generator post initialization context as parameter. All that is needed to make the generator output available for the consumer is to call the add source method on the incremental generator post initialization context. This method takes two strings as parameters. The first string is the hint variable and the second string is the marker source variable. This is everything that is needed to generate our marker attribute. To debug the generator, go to your generator debugging project and add a test accordingly to the test framework of your choice. Since I'm using XUnit, I have added a class named myGeneratorTests and added a void method called debugMarkerGenerator and given it the fact attribute. In this method, I first create a new instance of the marker generator. I then call the runDebugging method with an empty array of syntax trees, as well as an array containing the marker generator instance as parameters. Now, if I place a couple of breakpoints and run the test in debugging mode, I am able to step through the generation process. A new instance is created. We then programmatically create a new compilation. Then we hit the generator. And then we return the result. If we take a look at the compilation result, we will notice a few different properties we could look at. But for this video, we will only use the generated trees property. The generated trees property allows us to see the output from the source generator. We do this by selecting the first index. Then in the bottom, select _text, and then on source, click the view button. As you can see, the source code for the marker attribute is now part of the compilation. One thing to keep in mind is that despite the output being added to the compilation, it might still be invalid C#. This is one of the reasons I also recommend using a debug consumer. I have added a class called foobar to the consumer. Foobar contains some methods that has the onDispose attribute. As you can see, IntelliSense does not recognize the attribute. This is because the generator has not yet been run for this project. If I run the project, you will see that it runs just fine. But you might also notice that IntelliSense still does not recognize the attribute. I believe this happens because the generator is located in the same solution as the consumer. If I restart Visual Studio, you will see that the attribute is being recognized. This confirms that the generator is outputting valid C# code. But what happens if the output is not valid C#? In order to show that, I have removed a semicolon from the generator's output. Visual Studio is now telling me that I'm missing a semicolon. And when I try to run the project, I will get a build error. And even though the output isn't valid, if I restart Visual Studio again, the attribute will be recognized by IntelliSense. But the error still exists. The next step is to actually use the marker for something useful. As you can see, I have added a new generator class called onDisposeGenerator to the generator library. This class has the generator attribute and implements the INCREMENTAL generator interface, just like the last generator. But before I get into the nitty-gritty on how this generator works, let's first add a new method to the debugging project. That way I can step through the code as I'm talking about it. Just as the last one, I first instantiate a new instance of the generator class. But this time I also need to add some code that uses the marker attribute, otherwise the generator has nothing to generate from. To add the code, I first create a string that contains a simple partial class called foobar. Foobar has 3 different methods that uses the marker attribute, but written in different ways to make sure that the generator can handle those scenarios. Then the code string is passed to an instance of syntax tree, using the static parseText method from the C# syntax tree class. Just like in the previous example, we call the generator debugger.runDebugging method to run the debugger. Except this time, instead of an empty array of syntax trees, the array now contains the syntax tree with our source code. And the generator array contains the onDisposeGenerator instance. So let's take a look at the generator itself. Since the generator is dependent on the provided source code, we first need to find all the classes that has a method with the marker attribute on them. To do this, we call the context.syntaxprovider.createSyntaxProvider method. CreateSyntaxProvider's first parameter is a func that is used to check if the current syntax node might be relevant for the generator. The func takes a syntax node as its first parameter and a cancellation token as its second parameter. It then returns a bool. CreateSyntaxProvider's second parameter is also a func. This func takes a generator syntax context as its first parameter and a cancellation token as a second parameter. But it is up to you to decide the return type, depending on what is needed for your specific use case. In this example, I have created a class called onDisposedClassInfo that will contain the information needed for this generator. The needed information is the class name, the namespace, and a list of methods, including their sort order. For now, ignore the collect and where method calls. We will get into those later. The next step is to call the context.registerSourceOutput method. In the marker generator, we call the register post initialization output, but because we need the result from the syntax provider, we need to use register source output. The register source output takes two parameters. The first is the syntax provider we just created. The second is an action. This action needs to accept a source production context as its first parameter. The second parameter of the action is dependent of the syntax provider. In this specific case, the parameter needs to be an immutable array of onDisposedClassInfo objects. But you will see later on how this changes as the syntax provider changes. As you might have noticed, neither the syntax predicate filter, the transform syntax, nor the generate output methods has been called yet. These methods will be called once the current initialize method has returned. As you can see, once we have left the initialize method, the debugger will now stop at the syntax predicate filter method. The purpose of this method is to do a rudimentary check to make sure that the syntax node might be relevant for the generator. For example, if the syntax node is an enum declaration, then this method should return false because enums are not relevant for this particular generator. That way, we can avoid running the more demanding parts of the generator against irrelevant syntax nodes, and thus improve the performance. For this particular generator, we want the syntax node to be a class declaration. We also want the parent node to be a namespace declaration. This is a limitation I have decided to simplify the generator. Since the generator needs to know the class's namespace, I can simply take a look at the parent node. Lastly, we make sure at least one of the members of the class is a method declaration. If all the conditions are met, the syntax node is considered relevant and will be passed on to the next step. That next step is the transform syntax method. In this method, we have the opportunity to take a closer look at the syntax nodes that made it past the last step and extract all the necessary information. We know the syntax node provided by the generator syntax context is of the type class declaration syntax, so we will cast it to that so that we can access the class declaration syntax specific information that we need. Since method names and their sort order is one of the main things we need to extract, let's declare a list of ondisposed method info objects. To find the relevant methods, we loop through each member of the class declaration syntax to analyze and extract the information that we need. In this case, we are only interested in members that are methods. So the first thing to do is to check if the current member is of the type method declaration syntax. And if it's not, we continue to the next member in the list. If the member is a method, we need to check if that method has any attributes. If not, we move to the next member in the list. If it has attributes, then we need to find out if the marker attribute is one of them. To do that, we first need to get the semantic model of the method by calling the syntax context.semanticmodel.compilation.getSemanticModel, and then pass the current member syntax tree as a parameter. Then from the semantic model, we can get the declared symbol of the member by calling the getDeclaredSymbol method and pass the current member as the parameter. If the returned declaration symbol is not of the type iMethod symbol, we simply move on to the next member. From the iMethod symbol, we can then call the getAttributes method that returns an immutable array of attribute data objects. We can then loop through that array to see if any of them is the marker attribute. Inside the attribute loop, we'll take the current attribute.attribute class as a string, and then check if the fully qualified marker name contains that string. And again, if it doesn't, we move on to the next attribute in the list. By doing the check this way, it doesn't matter what style is used to write the attribute in the source code, since they will all be matched this way. Once we have found a matching attribute, we can create a new onDisposed method info object and set its method name property to the outer loop's method symbol.name property. We now know the name of the method. The next thing we need to know is the sort order. We can get that either from the current attribute's immutable array of named arguments or from its immutable array of constructor arguments. If they're both empty, we'll just use the int.max value as a default value. We will return to the named arguments and the constructor arguments a little bit later. Once we know both the name and the sort order of the method, add the onDisposed method info instance to the list. And once that is done, we can break out of the inner attribute loop, since we don't need to check the rest of the attributes. Once all the class members has been processed, we can then check if any of the members had the attribute. If none of the members had the attribute, that means that the class should no longer be considered in the generation process, so we can just return null. If at least one member had the attribute, we can then get the class name from the class syntax.identifier property. To get the namespace, we need to cast a class syntax parent syntax node to a namespace declaration syntax, and then get the name property. We now know the class name, the namespace, and the methods that contains the marker attribute, so we can then return an onDisposed class info object containing this information. At last, the generator output method is called. This method takes a source production context and an immutable array of onDisposed class info objects returned previously. This is where the final output for the generator is created. To do that, we'll loop through each instance of onDisposed class info in the immutable array. Inside the loop, we'll first order the methods by their sort order. We then create a unique hint name, and then create the code output for that class. To create the code output, we pass our code string using the sourceText.from method. At the end, we add the generated code to the source production context by calling the addSource method and giving it the hint name and the generated code as parameters. Now, if we take a look at the generated code, you might notice that the method calls inside the dispose method are not in the correct order, even though the source code did provide a sort order. And you probably remember I talked about the named arguments and the constructor arguments. One of the downsides to doing the debugging the way I'm doing it is that for some reason that I don't know, the attribute data object is not able to extract this information during debugging. This is another reason I think the debug consumer is very convenient to have in the solution, because if I run the consumer, you will see that the methods are in fact being called in the correct order. These kind of things sometimes happens when working with source generators, and because of that, I will show you another way to debug. It is possible to attach a debugger to the generator without having to programmatically create a compilation. By calling the debugger.launch and debugger.break from the system.diagnostic namespace. However, I don't recommend using this approach unless you have no other choice, since it makes the Visual Studio behavior very inconvenient. If we run the consumer project now, you can see that the constructor arguments and the named arguments now have values. In the previous segment, I skipped right over the collect method call. The purpose of this method is to bundle all the found objects into an immutable array. This array is then passed on to the generate output method, and that method then has access to all the found objects for its generation. And since the generate output method gets all the objects at the same time, it will only be called once. If the objects are not collected, instead of an immutable array of the object, the generate output method will need to accept the object itself, and the method will then be called once for each object found. Whether or not to use the collect method is a determination you will need to make based on your specific use case. Besides the collect method, we also have a where method, a select method, and a select many method. Unless you're completely new to C#, you will probably know these methods from LINQ. Just like in LINQ, the where method is used to define some condition that must be met in order for a given object to be included, similar to the first argument in the create syntax provider method. The select and select many methods are also similar to their counterparts in LINQ. They provide a way to extract information from the source object, like the second argument in the create syntax provider method. The reason that both is a select and a select many method is that the select method returns a single object, whereas the select many method returns an immutable array of objects. There is no limit to how many of these method calls you can include, but do be mindful of the generator's performance. One thing I briefly want to touch upon is the with comparator method. It is possible to attach a custom comparator to the select, where, and select many methods. The comparator is used by the underlying caching system to detect if a syntax node has been added, modified, or removed. The reason for this is again for performance reasons. We only want to run the node transformation when a change has happened to the node. Unfortunately, I could not think of a good example for the use case of a custom comparator. But to create a custom comparator, all you have to do is to create a new class that implements the I-equality comparator interface for the type of node you are working with. Then to use the custom comparator, you pass an instance of the comparator class to the withCompare method. The next method we'll take a look at is the combine method. There isn't really a lot to the combine method. Essentially what it does is to combine a node with something else into a tuple. In this example, I have combined a node as a class declaration syntax with the compilation. If we call the select method after the combine method, we can see that the result of the combine is a tuple containing the class declaration syntax and the compilation objects. It is possible for the generator to read and make use of text files that has been added to the consumer. To show this, I have added a text file called Bob to the consumer project. The file contains the following text: Bob likes pizza, swimming, and warm summer nights. The additional text generator will then match the Bob class with the Bob text file and add a method to the Bob class that prints the message to the console window. You might have noticed that the print text method is not being recognized by IntelliSense, and if you try and run the debug consumer, you will get a compile error. The reason for this is that we first need to tell the project that bob.txt is an additional file. This is done by adding an item group to the CS project file. Inside the item group, we add the tag additional files and tell it to include bob.txt as an additional file. If we don't do this, the generator won't be able to use the file. Now that we have done this, we can run the project again and see that the text has been printed to the console. To access these additional text in the generator, all you need to do is call the incremental generator initialization context .additional text provider. Since we have already talked about the combine, collect, select, and where methods, I'm going to go straight to the generate output method. The generate output method accepts an immutable array of tuples containing the matching class declaration syntax and additional text objects. Then, to actually get the text from the file, call the getText method on the additional text object. To debug the additional text generator, the first thing we need to do is to add a mock additional text class to the debugging project. The mocking class needs to inherit from the abstract class additional text. Since the additional text class is an abstract class, we must provide overrides for the path property and the getText method. We can then use this class to simulate additional text. But we also need to update our generator debugger.runDebugging method to accept the additional text and then use them in the debugging compilation. To do that, we add a nullable IEnumerable of additional text with the default value null to the method signature. In the method body, we check if the IEnumerable of additional text have a value. If it does has a value, we'll use it to create an immutable array of additional text, and then add that array to the generator driver using the add additional text method. If the generator needs access to information about the consumer, such as language version, if it's in debug or release mode, or other stuff of that nature, it can be accessed via the pass options. To get the pass options in the generator, we need to call the incremental generator initialization context.passOptionsProvider. To add pass options to the debugging compilation, we again need to modify the runDebugging method, this time by adding a nullable pass options parameter with the default value null. And in the method body, we call the withUpdated pass options method on the generator driver with our own pass options as parameters if it's not null. To create our own instance of pass options, we can create a new C# pass options object. This will allow us to define stuff like language version, and so on. The generator might need to know about the consumer's metadata. Let's say we need to change the code generation depending on, for instance, a specific library being available. To access the metadata information, you will need to call the metadata references provider on the incremental generator initialization context. By doing that, you will get access to the compilation's metadata references, which, as the name implies, contains the metadata. To be able to use the metadata in our debugging, we add a nullable IEnumerable of metadata references with the default value null to the run debugging method's parameters. We then replaces this null value to use the new parameter. To create a metadata reference object, you can use one of the static create methods in the metadata reference class. Another need the generator might have is to change how it behaves depending on certain rule set and their values. You can define such a rule set by using a custom .editor config file. The rules from the editor config file can be accessed from the analyzer config options provider on the incremental generator initialization context. Then, to get the options value, we can just call the try_get_value method on the analyzer config options provider using the rule name as parameter. To debug the analyzer config options, we first need to create a mock implementation of the abstract class analyzer config options that we can then give our desired key value pairs. We also need to create a mock implementation of the abstract class analyzer config options provider that will be used to provide our mock analyzer config options. And just like the last few segments, we again need to expand the parameter list of the run debugging method, this time with a nullable analyzer config options provider that has the default value null. In the method body, if the analyzer config options provider is not null, we call the with updated analyzer config options method on the generator driver with our own analyzer config options provider as the parameter. Now that we have a way to set up the rules for the generator, we also need a way to inform the users when they break those rules. So far in the analyzer config options provider generator, we have just thrown an exception when a rule was violated. And even though the exception message should show up in the output window on build, it is still not the best developer experience. Instead, I have added a method called addDiagnostics. In this method, we first create a new instance of diagnostic descriptor. This object is a description of the diagnostics you want to convey to the developer, and it contains things like title, message, severity, and so on. We then call the static create method on the diagnostic class to create a new diagnostic object. The create method needs our diagnostic description and the location of the syntax node. To report the diagnostics, we call the source production context.reportDiagnostics method and pass our diagnostic object as a parameter. If we now add a new editor config file to the consumer and updates it with the custom rules, you will notice that the diagnostics will show up in the error list. If you just double-click the file, it will open a window where you can set the values for all the default rules that come with Visual Studio out of the box, but not our custom rules. In order to actually open and edit the editor config file as a text file, you will need to right-click on it and select Open With, and then select Source Code Text Editor. The last thing I want to show you is the forAttribute with metadata name method. forAttribute with metadata name for the most part works just like the create syntax provider method, except that by using this you can make sure that the syntax predicate filter and the transform syntax method are only run for syntax nodes that has a specific marker attribute, without having to implement the logic yourself. The first parameter is the fully qualified name of the marker attribute. Then, like the create syntax provider, it takes the syntax predicate filter and transform syntax methods as its second and third parameters. But the transform syntax method needs a generator attribute syntax context instead of a generator syntax context as its first parameter. The incremental generator initialization context also has a method called register implementation source output. This method does the same thing as the register source output. But semantically, you're not guaranteed to have the generated output available for you in the IDE. This is up to the IDE to decide if they're going to expose the output. The syntax provider also has a method called with_tracking_name, but I was never able to figure out what the purpose of this method is. Source generators are powerful tools that are perhaps underutilized. I think the reason for this is that the documentation is pretty poor and sometimes outdated. Because of this, the learning curve becomes far steeper than it needs to be. This is one of the reasons I decided to make this video. I would also like it to be possible to access content files and embedded resource files in the generator. Imagine, for example, if you added JavaScript files to a Blazor web application and then was able to generate the code that calls that JavaScript. I really think that would take the generators to the next level. In order to keep things simple in this video, I just use strings for the code that the generators are generating. But in a real-world scenario, I would probably use the syntax node objects we are already working with to get the source information. If you want to learn more about how that is done, take a look at these videos from the YouTube channel Coding Tutorials. The syntax visualizer in Visual Studio can also be a helpful tool as it allows you to inspect the syntax you're working with. Thank you for watching this video. Feel free to do the like and subscribe thing, and I hope to see you again soon.